Laurentian University. She's a PhD student there presently. She got a BSc from Carleton, and she's had some experience, worked for Quadra FNX Mining at one point, and has worked at the Geologic Survey of Canada as well. Her talk is entitled Structure and Stratigraphic Characterization of Chisel Basin, with co-authors Bruno, LaFrance, and Harold Gibson, both professors at Laurentian.
All right. Thanks very much, and thank you very much for having me today. So just a quick outline of what I'd like to cover today. I'm going to give a little bit of background on our thoughts of what this chisel sequence or interval that Al just talked about could have looked like at the time that it formed. Just as a very quick background. And then the rest of the talk is kind of divided into two parts. So the first part, I'll establish the main deformational events influencing the Snow Lake arc assemblage, and then I'll take those events and apply them to some of the VMS deposits to see how those deformational events may have influenced the geometry and current location of those deposits. So again, you're all very familiar with this diagram. Just to reiterate, I'll be focusing in on the ore interval on the chisel sequence that Al just discussed. And once again, same diagram that you're all used to seeing. Just to show the relative location of these deposits, and again, I will discuss Photolith very briefly and current thoughts on why it is where it is. So the chisel sequence ore interval occurs between the Powder House dacite and Three House mafic volcaniclastic units. So those are the two units to really keep in mind as the primary footwall and hanging wall in a very broad sense. And it consists of bedded primary and resedimented primary pyroclastic deposits, so a lot of felsic and mafic tuffs. It represents a transition from a more felsic regime into this more mafic regime, so often we do see interbedding of both felsic and mafic tuffs, as well as rhyolite dome development associated with these VMS deposits. So just a few images to kind of give you an idea of what this ore interval looks like in the field. As I mentioned, it consists of primary and resedimented primary pyroclastic deposits, and it is a depositional basin. So in order to form these VMS deposits, there has to be an interval of relative volcanic quiescence. So we can't really have much explosive volcanism going on because it doesn't provide a conducive environment to actually accumulate these sulfides at the seafloor or subsea floor. We see both proximal and distal lithofacies of the felsic domes associated with mineralization, as well as the sulfide deposits. And through mapping in the overlying Three House mafic volcaniclastic unit, so that hanging wall unit to the deposits, we actually see that certain areas may be emergent, so that water depths may be so shallow that certain parts are above the water. And we see as well successive episodes of subsidence. So just some images, again, these bedded tuffs, more of an intermediate composition here, and some synvolcanic faulting within these tuffs. So this is really important because subsidence, as both of the Als have mentioned, is very important. We need these fault structures as a conduit for the fluids to actually form these deposits. So synvolcanic faulting is really good to see. And again, more synvolcanic faulting offsetting the beds here. And we see a definite mixing of different class types. So some of the class types are actually sourced from units underlying, stratigraphically underlying where we find this outcrop. So this is what we refer to as the Lost Lake outcrop. It represents a very, it's a depositional low in the basin. And the fact that we're sourcing units that are stratigraphically below this unit suggests that there might have been quite a significant degree of subsidence. And finally, a few more photos again of this interbedded tuffs, and as well some rhyolite, beds of monolithic rhyolite volcaniclastics, suggesting that there are rhyolite domes nearby. So this is a little bit of an arm wavy figure, but this is kind of just to give you an idea of what we're starting to think this basin could have looked like. So this is, I'll touch very briefly on gold enrichment and metal content because that's one of the main ways that we've come up with this model. So essentially all of the deposits in the chisel sequence have different copper over copper bliss zinc ratios as well as different gold grades. So if we look at the copper over copper plus zinc, as I'm sure you can figure out, the higher the number, the more copper rich, the lower the number, the more zinc rich. Now, if we take this and think about boiling, which Al-Ghali discussed, it can be a very efficient mechanism for both separating gold and potentially copper, as well as precipitating metals in the subsea floor. So what we often see in some of the deposits with a higher copper over copper plus zinc value is that there's a zinc-rich lens as well as a copper-gold-rich zone. So a current thought is that constraints on metal content in the deposits might be a result of water depth of the deposits. So a shallower water depth could produce a more zinc-rich deposit because all of the copper and gold would have possibly already been precipitated at depth if we consider the boiling curve. So boiling will be suppressed as you increase water depth, and as you bring it up to surface will occur at a lower temperature. So again, as I just mentioned, these variations may account for differences in gold content. So don't have to dwell on this too much. It's just to give a little bit of background of how we actually come up with a figure like this, and just to give you an idea of what the environment would have looked like at the time these deposits were forming. So now if we switch gears a little bit into the structural side of things. So there are three main deformational events influencing the snow lake arc assemblage. D1 manifests itself as tight isoclinal F1 folds, and there's really no preserved S1 foliation. In the burntwood turbidites that Al Bales mentioned, we do see some S1 preserved as inclusion trails and garnets, but unfortunately volcanic rocks and turbidites have very different metamorphic conditions, so the inclusion trails and garnets in the volcanic rocks are actually an S2 fabric, so we don't really see it preserved too often in the volcanic rocks. D2 manifests itself as a very strong S2 foliation, and this is the dominant planar fabric in the area. We also see an L2 lineation and larger scale F2 folds. So difficult to identify the outcrop scale, but on the map pattern we do see good F2 folds. And finally, D3 is an upright, open to closed, northeast striking F3 fold. So this is the main deformational event that kind of gives everything that nice curve that we see in all the maps of the Snow Lake arc assemblage. There is a D4 as well, but I haven't mentioned it here because it's not too important for what we're looking at today. So just a few nice field photos to actually see what this looks like and what I'm talking about. So F1 folds can be kind of difficult to find, so we were really lucky finding this folded dike in the field. So it's a plagioclase spheric mafic dike intruding into a rhyolite body, so we see a good F1 fold being cut by this S2 fabric. And again, so S2 commonly flattens any clast. There's quite a bit of volcanoclastic material, as I mentioned, in this area. So flattening of clasts, elongation of clasts are all D2 structures or features. And this is again being refolded by this broad open to closed F3 folds. And again, we see F3 actually folding these flattened clasts. So these are the inclusion trails that I was talking about. So we can see the quartz inclusion trails in the garnet here. And this is actually an S2 fabric with pressure shadows along the S3 fabric. And again, this photo is really nice because you can actually see the S2 coming through and cutting through the garnet. So that's how we can tell that it's not actually an S1 in these particular volcanic rocks. It's actually the preserved S2. So it also fits nicely because peak metamorphic conditions were syn to late D2. So that fits nicely with our story here. And finally, just to see what that strong lineation looks like. So these rocks are almost an L tectonite with this very strong L2 lineation. So switching gears once again, we'll look at how these main deformational events have actually influenced the current geometry of the deposit. So we'll start with the Photolith Deposit, which you'll remember sits within kind of a strange stratigraphic position within a rhyolite body here. So what we've done is we've compiled drill hole data and historical logs, and we've produced a cross-section cutting through the deposit. So it's fairly rough, and there are some maybe enhancements that need to be done. But what we see is that the deposit seems to actually sit at the contact between two different volcanic units. more work needs to be done to actually correlate these potentially with rocks either in the lower Chisel sequence or the upper Chisel sequence, but they're very distinct based on zirconium-titanium ratios, and they cluster quite nicely. The other thing we notice is that there's a zone with very low alteration between the two ore lenses. So there's a copper-rich number 1 lens, so very copper-gold rich, and then a zinc-rich number 2 lens. So potentially what this could represent is a fold structure actually folding the deposit. We may have lost the fold hinge, and it's transposed a copper-gold stringer zone against the more zinc-rich lens. So whether this still represents a different stratigraphic position altogether is still a little bit up for debate, but it certainly doesn't just sit within one massive homogeneous rhyolite body as it sometimes looks like it could. So switching up again, we'll look a little bit at the Lalor deposit. So just build a little bit off of what Al talked about in his talk. So I'm going to use Al's cross-section and just look a little bit at the structure on top of that. So here's the cross-section that Al showed you. And as he said, there are two issues that you can see right off the bat. So the first being this juxtaposition of the steeply dipping strata against the more shallowly dipping strata. And we can't really carry these units through into the footwall of this potential fault very well. The second issue is the strange geometry of these sulfide lenses. So it's a little bit different, and we'll investigate that first. So if we think very broadly about metal zoning in a VMS deposit, typically higher temperature fluids will carry your copper, so chalcopyrite, pyrrhotite, and then as the fluids decrease in temperature, they'll lose those copper mineralization and become more zinc-rich. So we see a zonation in the sulfide lens of a more copper-rich core out towards a zinc-rich exterior. This is very generalizing quite a bit, but we can kind of use this and look at the metal zonation that way. So what we'd expect to see are copper-rich upflow zones. Now, what we can do is look at metal zoning in these sulfide lenses to see if we can identify any of these upflow zones within the lenses. So these are block models of copper over copper plus zinc again. So blue would be a lower value, very zinc-rich, moving up to red being a higher value, so very copper-rich. These lenses look a little bit different than what they do in the previous cross-section I showed you, but that's just because this is a resource model, so it's not the true geology, it's what's mineable. So just keep that in mind. So here we have a block model of the lower lenses, and we see they're very blue, mostly zinc, not a lot going on. If we move up and look at the block model of the overlying lenses here, we start to see that there are some hot spots that could potentially be upflow zones. Now looking at this particular lens, so looking down upon the lens, and then if we were standing beneath the lens and looking up, we again see that there's definitely an upflow zone that doesn't penetrate through to the other side of the lens. So this seems to suggest that this lens is upright because the upflow zone would come through but hasn't penetrated through all the way. As well as if this were a homoclinal succession, we should see the upflow zone all the way through these lenses, but we don't. So that seems to suggest that the lenses could potentially be folded. So possibly we're looking at some sort of anticlinal structure in the footwall here. The other thing that I've thrown on here, and Al Gali mentioned, is just sodium. So background rocks on the seafloor will be spilitized. So basically all that means is there's an overall background addition of sodium to seafloor rocks. When you hit those rocks with a VMS alteration system, they become very depleted in sodium. So what I've done is just plotted the straight sodium values, and so this zone represents sodium values less than 1, and it's a very rudimentary way of looking at alteration, but it does show a very nice alteration system, again, that seems to follow with the potential fold in the footwall to this structure here. As well, so these could potentially be faults, as Al mentioned. I've put a fault in here as well because if we think about our typical sequence from Moore Lake into Powder House and then into overlying Three House, and then we also think about the fact that this lens we've determined is upright facing based on metal zonation, it would be very strange for it to be sitting below the Moore basalt. So not 100% sure these are Moore basalts, but the chemistry is very similar to Moore basalt. So as well as it wouldn't be unusual to find a fault right at the contact with a very strong alteration system mineralization. It's a good place to hide a fault. So if we zoom in and look a bit closer at what this fault actually looks like, we see that it doesn't really look like a whole lot. It's not as obviously a fault as we'd hope it would be. There does appear to be a little bit more of an alteration zone where this fault occurs, as well as a mixing potentially of rhyolite blocks as well as more mafic blocks of the underlying unit. So what this could represent is a brittle fault that has then had alteration superimposed on top of it. So it could be a very early structure, potentially a D1 or D2. Again, zooming in, there's not a whole lot about it that really screams fault unless you're looking for it, but it wouldn't necessarily be ruled out as completely not being a fault at this point. And another way that we can determine that this could potentially be a fault is this is what that contact typically looks like. So what we're looking at here is a transition from the rhyolite down into the underlying unit, whereas typically we see the rhyolite transitioning into the three-house mafic volcaniclastic rock. So that change in contact relationship suggests that potentially there could be a structure here. So now moving on into possibly a more ductile fault. It's possible that this fault actually is we see it at surface. So looking at it in the field, this is a more obvious fault. This is what we'd like to see. So it could be a bit strange that the fault is brittle at depth and ductile at surface. So we could be dealing with two different faults. But at that contact, this is the relationship we see. So this is the contact between a rhyolite into a three-house plagioclastic intrusion. So this is what that intrusion looks like about 6 meters away from the contact. And right at that fault contact, we see that it's quite beaten up. And it appears to be more of what we would typically associate with a ductile fault. So finally, just looking very quickly at the surface geology, a lot of mapping has been done through this section here. And unfortunately, none of the facings are incontrovertible. But it's possible that there are facings to the east in this zone here, as well as there are good facings to the west here. So potentially we're actually dealing with either a very tightly folded sequence, or again, we're looking at these thrust repeats in the fold and thrust belt that Al mentioned. So if that were the case, if these are very tightly folded packages, these would be more of a F1 fold, which would have to make these structures in here D2 structures, so a D2 fault and an F2 fold in the footwall. So in conclusion, there is a strong structural control on both the geometry and location of these VMS deposits, and D1 and D2 really do seem to be the dominant structures controlling this. D3 changes the shape of the lenses a little bit, but it doesn't influence entirely the location of these deposits. We may actually have repetition of this ore interval. If we do have these thrust repeats, we could be seeing the ore interval in more than one location, as well as the structural control can actually help in cases to define the limits of the deposits. As I showed with the sodium depletion, it could actually help to cut off where the mineralization goes. And that's it. Thank you very much.
Any questions?